Good afternoon, everyone. My name's Hugh Sanderson. I'm going to be talking about the CPP backend for Haxe. The title Haxe girt by C++. I think the Australians amongst us will recognise the quote. It's from the Australian National Anthem, and it uses the word girt, so you've got to respect that. So you don't see that much these days, so I thought I could use it too. So I'll be covering a couple of things. I'll start slow and get boring. I'll talk about the overall architecture, then I'll talk about some gory details and some things you might need to know when you're thinking about implementing things one way or another, and some eye to the future. Why did I create the back end? Well, the original motivation was speed. I tried to do some physics stuff with Nico. It was just too slow. It's fine for certain tasks, but as soon as you need to do any kind of number crunching and looping, it was too slow. So the current state of affairs is that it's probably at least 10 times faster than Nico for the numerical style applications. 2 to 3 times Flash and V8. I guess it's a bit debatable, but I think it's clearly about twice as fast as Flash. And it's not as good as handwritten code, but it's not that far behind. So I call it about half the speed, but again, that's debatable and depends on applications. So the basic architecture starts with the user code in the top left corner there. The .hx files are the ones that you guys write. It then gets combined with these orange HXCPP files, which are from the standard library code. It gets all munched through the Haxe compiler. The bit of interest that I've written is the girt.ml, and it produces this set of outputs: the CPP files, the header files, and the build.xml files. And at this situation, the Haxe compiler's job is done, and it hands the operation over to the HXCPP build tool. Here, the build tool takes in these generated files, adds in some of its own for good measure, and uses a compiler or SDK that you have installed on your machine to produce a native executable. There are also native NDLL files, DLL files, that can be used as runtime. The compiler and the SDKs, obviously we don't provide those, but there are many that we do support, and there are plenty of free ones that you can use to work with the CPP compiler. So the girt.cpp.ml is the bit of code for the CPP specific bit of code inside the Haxe compiler that I've written. Okay, so the back end is implemented in a single file, so that I guess I can keep my damage to a minimum on the other targets. It's about 3,000 lines of camel code, which is getting up there, I guess, sort of more than you can take in one sitting. And I gained most of my OCaml knowledge from the existing Haxe compiler code, so I've probably got a bit of a French accent if you go through the code. And it's evolved well beyond its initial design, so some of my normally high programming standards may have slipped just as I had to put a hack upon a hack as things evolve. So the HX library files are the ones that get distributed with the compiler, and they bear a remarkable resemblance to the Nico ones, and that's no coincidence because I copied them, obviously. Actually, with the new announcements today of the unification of a lot of the libraries in 2.09, it actually makes a lot of sense that I copied it. So laziness is a virtue in this sense. In this case, I always believe that when I'm a programmer. And what these files mainly do is use various small little delegations to the actual CPP runtime that gets compiled into the final executable. There's not a lot of logic or intelligence in these files. The the code generated by the backend is designed to be readable, readable in a CPP sense, which is not to say absolutely readable, but as best we could do, and to have a high correlation to your Haxe code. So if you've written while something, I've tried to write while something. If you've written switch something, tried to output switch something. So that you can pretty much follow along. And it's written, there are some things that just don't map to the C compiler, like local functions, don't exist in the standard C version, although C++11 is bringing in some stuff that actually may have fitted in quite well. But to move to that would introduce a whole level of incompatibility with compilers. We're still using some compilers that are 10 years old, so it's going to be a while before we could confidently use any of these new features. So some things like local functions actually come out like a bit of a dog's breakfast. They just, macros and hash if this all over the place, but that's something we'll have to live with. I try to use native facilities wherever possible. So I use native virtual functions, native RTTI, native exceptions. I'm hoping this will make it easier to interop with other libraries as well. I also use templates to do casting, so you can actually quite naturally map something equals something in C++, and if it was like a float int conversion or a downcast or whatever, it will just it'll work according to the C++ rules, pretty much like it works according to the Haxe rules, which keeps the two closer together. I also use a lot of macros for doing some of the slightly unusual stuff, or for doing code positionings and things. And the idea here is that guys like you who want to tinker with some of the aspects of the compiler, it's going to be easier for you to change a macro than it is to change the OCaml code and recompile the OCaml. So I try to have as much kind of accessible, make as few hard decisions as possible in the OCaml code, and leave all the stuff to the CPP code where it's more accessible for tinkering, and patches as well. So I've had quite a few patches come through from people because they've had the ability to go and edit it. So I think this has been quite a good thing, even if you don't like macros. So the runtime files are distributed with the HXCPP Haxe lib, and they provide the basic runtime. So they've got all the facilities, garbage collection, some file IO stuff, threads, strings, arrays. That's all in there, and it all gets compiled by you with your compiler, which is good for debugging, and it's good for if you want to change something, you can put a printf in one of the functions just to see what's going on. So providing it in source form, I think, has been a bit of a win. Of course, every time you create a new CPP project, you have to recompile these files for the new project. Generally, you only have to do this once per project, but it can still be a bit of an overhead. So I've had some ideas with maybe some object caches where if you've compiled the file once with identical compiler settings and identical input files, the output should be identical, and therefore I should be able to cache it. I think GCC may even have some of this stuff in it built in as well, so I might be able to hook into that. But I think the advantages of providing the runtime in source form outweighs the disadvantage of having to compile it for every project. So the runtime DLLs come in binary form, although there is source included if you need to compile them up yourselves. And again, they mirror the Nico ones. And again, it's because I just copied the Nico source code. But I had to change. There are a few differences between the ways HXCPP interacts with external DLLs and the way Nico does. So while I can copy the source code, I still need to recompile them, and I can't just use the Nico binaries. Although the converse is actually true, is you can use CPP compiled DLLs with Nico generally, and that's one thing I do with NME. It's a universal DLL for Nico and CPP. So the build system is responsible for taking all your files and combining them with your compiler or SDK, and generating the executable. So in a lot of ways, it's like a make system or the ant build system, but because it uses Nico, which is comes with every Haxe install, so I can be pretty sure that no one is going to have to run off and go, oh, well, I need to install Nico now to get this to work. It really limits the dependencies to practically zero, which I think is a good thing. And the whole build system is built around just simply setting variables and conditions, and it's quite easy to hack and quite easy to create a new to configure a target or add a new compile flag. So I think it's been quite a useful contribution to the whole system. Easy enough that we've had other people, particularly Joshua, contribute actual whole back ends, like the BlackBerry and the WebOS, are user submitted contributions, and they're really only 50 lines of code that's pretty easy to read. So if you want to get in and change some compiler settings or make a new compiler, it's actually pretty straightforward. And you can see here, these are the targets that we've successfully compiled to, and it's pretty much anything that has a C compiler we can compile to, or C++ compiler I should say. The notable exception here, I haven't put the NACL Google native client in, but that's probably on the horizon soonish. So now I'll get into some implementation details, and if you're not technical, you could spend some time, digest your lunch, and I'll get on with the rest of it. So what makes the CPP backend fast is the strong typing. Not as in hitting the keyboard, but so whenever the compiler knows the exact type of the variable that you're using, it can perform the optimizations, it can parallelize them, it can do them out of order, it can use registers, and it just loves it when it knows the exact type of the variable. When it doesn't, which is in Haxe when we have a dynamic variable, you have to look up a variable by name, the performance immediately drops. If we were to use dynamic everywhere, it would be much more like a scripting language and scripting language performance, we'd lose all the advantages. And in this case, laziness is not a virtue, so unfortunately I've had to do some work to get it to be as strongly typed for as long as possible. And knowing where the back end is using strong typing and not using strong typing should give you an idea of what constructs are going to be fast and which ones are going to be slow. So just in my discussions, a couple of concepts with the typing. I refer to stuff as dynamic, and in Haxe you can actually have a variable which you just call dynamic. And this is just to say that it's an object that you know nothing about, and you can perform certain operations on these objects, like look up a field by name, and you're just going to get another dynamic out. So the compiler can't really do anything here except look up stuff by name. If it knows the type of a class, and you refer to a variable x of that class, it knows, well, actually it's 14 bytes from the beginning of the structure, bang, it gets it there. If it's dynamic, it's got to go, okay, where's the variable x? It's got to go to a table, find x, and go, oh, okay, now it's 14 bytes. It can carry on. The other concept is boxing, and this happens when a non-class variable must be referred to as dynamic, and the non-class variables there are bool, int, float, string. And in order to treat them as a dynamic, you actually have to allocate off a little dynamic structure just to manage this particular value. And that is the probably biggest problem with the performance. And it's also where you can get some strange things like an array of integers, or sorry, not an array, a list of integers can be slower than a list of other objects. It's because the other objects are already effectively dynamic objects, and the integers you have to actually create a little dynamic to handle them. So that's boxing. Wherever an integer is passed to a dynamic, it will be slow. So where currently is dynamic stuff used? Well, it's used wherever you have a parameterized class, like here, some class T. If the T variables are stored in that class, they really have to be dynamic. There's just
there's no other way that I could store both, because t might be an integer one day and it might be a, string the next. The common denominator is dynamic, so I have to store the variable in the dynamic. Now, Haxe actually has a facility to automatically generate whole new classes from your templated class. So if I go some class integer, it will actually go, I'll make a whole new class called some class integer, not parameterized. And in that case, you're back to full speed again, because it's duplicated the code and made a specific integer version of it. Now, so I've had some ideas here about where performance could perhaps be improved. It might be possible to create up to 4 or 5 instances of the class, rather than one class per type that you use it with, for the particular value types, and therefore have a compromise between having to create a new class for every and have to specialize the template for every type you want. You really only need it to do it for the particular value types, because normal object types are actually pretty much the same speed, because they don't have to be boxed. And then a slight variation of that is bool, int, and float can all be represented by a float without loss of information. So perhaps I could just have a floating point version of those. The other big one is functions that you store in a variable effectively become dynamic. So when you pass like an integer to one of these functions, it gets passed as a dynamic, again creating all the problems. Now, I can't really create a new function class for every different type of function there is, because if you have a function that takes an integer and then one that takes a class A and one that class B, I'd need to have a different type of function for each of these situations, and you'd end up with hundreds of different function types. It might be possible to, for example, do either just float or dynamic, and maybe only up to the first 3 arguments I could make fast, and after that it becomes dynamic variables. So there's another open issue about speed, and you'll particularly notice this in NME with the CFFI, where we make calls into the DLL. They pass in dynamic variables, and immediately if you try to pass an integer in, there'll be a slowdown. When you use this construct here, where you've got use your squiggle brackets to define a type in a function, I call this this is a type restriction, so that's saying that bar has this function called run. In this particular case, I may actually be able to create a fake interface and then automatically implement that interface on everything that calls this function, and that would get speed back up to full. And similarly here, the bottom case, we've gone bar that x is 20. That's an anonymous function, and it may be possible to actually create a fake class in this case to hold the x value, and again bring that there up to full speed. So there are some ways where dynamic is being used at the moment that it might be possible to avoid it in the future. Arrays are actually probably the fastest way you can do things. Like if you have to choose between an array and a list in CPP, you should probably choose the array. Lists have the advantage if you're pushing things onto both ends and stuff. But the crossover point where it becomes better to use arrays, it would be quite a large number of elements, or worse to use arrays. This is because the arrays are pretty much optimized and are all fairly strongly typed. When you access an array using brackets I, it does a range check every time you do that. So there's that would why you would be potentially slower than native code. But there are some unsafe get and set functions you can use if you're particularly interested in speed and you know for sure that you won't be running over the bounds of the array. An array dynamic is another interesting one. I actually implement this fully as just a normal dynamic, because even if it is array of dynamic, then there's a bit of a loss there because you should actually be able to do full speed things. But if I need to pass in an array of bool to an array of dynamic, there's effectively no common denominator. Well, the common denominator is not easy to use. So I've switched over to array of dynamic. In itself, actually, will be slow to access. There might be something I can do there with an array base class, but I'm not sure if it'll be worth it in terms of speed. So interfaces, originally I implemented these using the normal C++ multiple inheritance constructs, but they turned out to be really quite painful to work out where objects were being referenced from the garbage collection, because they have offsets to the objects from various places within other objects. And I changed this to a delegation model, and everything was much nicer. So when you create an interface from an object, what it does is it creates a little glue object in between that just passes the function calls onto the real object. So interfaces themselves are now kind of little objects, and that's just made things easier as it's just sort of implementation detail, really. So biggest pain in my proverbial is the C++ order of operations. Haxe has it clearly defined that the operations, particularly like, for example, function arguments, should be evaluated left to right. So in this case, down the bottom here, I've got f of c blah 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 comma I. The expression on the left should be calculated first, and the expression on the right should be calculated second. But C++, trying to be nice to itself, has declined to guarantee the order in which it will evaluate these things. It's mainly because it's trying to optimize for speed, and when things are pushed on the stack, they're usually pushed on right to left, which is the exact opposite of what we want. So there might be some stuff to be able to tease these expressions apart and use temporary variables to calculate some of the partial expressions and then assemble them back together in the correct order. But it's pretty hairy. If you look at this expression here, evaluates I++, which may or may not be 0. If it is zero and it doesn't enter this bit here, then if I've calculated any of those variables in a temporary variable, then I've wasted the calculation, and not only that, I've increased I, and it will all be wrong subsequently. And similarly with this OR expression here, if the expression on the left evaluates to 0, then it will do the expression on the right, otherwise it won't. So it's an extremely difficult problem, as I think anyone who tries to write a target will understand. Currently this is still effectively a bug in C++, that you have to be careful of the order, that you can't expect the strict left to right ordering. So the foreign function interface has evolved from the Nico one. It's designed to be largely compatible with it, but it also has been designed to be more generic. Dynamic libraries are built, you can build them using whatever you like, but generally the HXCPP build tool is a good choice because it will make sure all your compiler flags and things work correctly. And it allows you to interact effectively using a completely different compiler version, so the API between the two is very simple and makes really no assumptions how the variables are stored. So in this case, we can write, for instance, the NME DLL. We can use it for Nico. I had it working with V8 and CPP, and potentially any of the other targets can implement the interface. This is also where the boxing issue comes in, because the API effectively involves dynamic variables. You also have to be a little bit careful, because I've been a little bit slack and made the DLL take care of some of the garbage collection and thread management. So you probably have to do a little bit of a read up if you're going to be storing variables in storing variables for later use, or using multi-threads in your NDLLs. I've also recently added some metadata magic where you can inject code into your CPP classes, into your functions, into the headers, into the beginning of a function or end of a function. So if you need to just call off, for instance, if you wanted to call printf directly, you could inject the code using a little bit of metadata, and this also lets you, if you need to do some kind of store some additional variable in your class that doesn't really match the Haxe syntax, you can use the metadata to do that as well. So garbage collection, actually, a lot of the performance of the back end will depend on the quality of the garbage collection. Originally I started off with the BOEM GC like Nico does, but I had trouble getting it to run very well on the ARM, and also as more and more targets come online, you would have to make sure that that library was also updated to match the new targets. The current system uses a kind of a homebrew system, and it only uses two assumptions: a standard stack layout, that is, things are pushed on the stack when you call a function, and that you can actually get all the registers to be pushed on the stack if you make a sufficiently complex function call, which is basically a virtual function with a lot of parameters in a different file. And so far so good, that those two assumptions actually have covered all the targets that we've hit so far. So that means that we don't have to do sort of bizarre system headers in order to get the garbage collector to work. It's mostly precise, which means it'll mark variables that it finds on the stack, but normal variables will be marked conservatively. And this allows you to have local variables in a NDLL file, and they'll also be found by the garbage collector. And that's been quite useful. There's a problem is that each thread that runs through the garbage collector needs to effectively clock in and clock out, so that the other threads don't wait for it when they need to do a collect. The compiler generates code that actually does the marking, so rather than having a data structure that describes how classes are laid out, there's actually a piece of code that it runs, which is pretty simple. And the garbage collection, there's plenty of scope for research and doing more work on this, and any improvements should directly be reflected in faster code for everyone. So I don't know if there's someone out there who loves garbage collection and wants to take it on as a project and make it 10 times faster and be a hero, but yeah, that would be nice if someone does. So looking to the future, we can't all be Albert Einstein, so you have to think about it. So obviously I'm supporting Haxe features as Nicholas comes up with them. Add new compilers as required, and then update the old compilers when Apple decide to move their compilers from developer to app or whatever they choose to do, or Google moves their NDKs around, so just keep those up to date. And these performance improvements that I outlined earlier, I'll probably get to those at some stage if I find a particularly bad piece of code that needs a speed improvement. The garbage collection, there's actually scope to do, even if your app is single-threaded. Oh, just in time. Yes. It's all over for me. Alright. So, I think I'm on the last slide anyhow. So, the garbage collection and, yep. I think I've gone grey. I think. Oh no, here we go. I'm on the last slide here. So, and then some other. Oh no, I've got one more slide to go. Zoom out. that, is it? No. No. Where am I? Oops, didn't want to do that, did I? Go to last slide. I need second last slide. Yeah. Okay. So the other things I need. Oh, power. Yeah. Yep.
It's good like that.
There we go. Look at that. Oh, it was on the last slide. Oh no. So yeah. So also I'm looking to do some instrumentation to improve debugging. So I actually put stuff in your code to help you either profile or visualize some of the memory allocations and usage, and a graphical view of the memory usage, so you can actually see how the objects are laid out in memory. All that information is there. It's just a question of accessing it. So I've got a little quick demo I can do on that if we've got time. How are we running for time? Yep. All right, so what I'm doing here is I'm starting up a little debug server on the local machine, listening on the local host, and then when I start up an application that has been compiled with the debug host set, and then it comes back into the debug server, and I can type continue. And then break stops it anywhere. So that's listed. So some basic debug information. Currently, that's all you can do: break, where, and continue. But it should be a logical extension to view object details and local variables and set breakpoints, just like a proper debugger. Yeah, so that's I guess a glimpse of where some of the instrumentation stuff might go. Any questions? Yeah, that's actually in any executable. Particularly, I guess the idea was for Android. So it'll actually fork over the Wi-Fi to your computer rather than over ADB. Android is like
for the debugger you saw, like, show us, is it possible to debug this way, like iOS application?
Yes, yeah. So again, because it uses a socket that it talks over, as long as your iOS device can find your local host, yeah, you should be able to do
So
debugging.
on the same Wi-Fi network.
Sorry?
On the same Wi-Fi network.
So, yeah,
It should work.
it should work. Yeah, yeah, yeah.
Hello?
Yeah.
Okay. So about the debugging, for example, iOS has the native debugger. Why can't we use that? Or
Yeah, so the iOS debugger actually is not too bad. You could well use that. I guess this has Android is currently quite tricky to get debugging going. There are some other things which potentially we can do. For instance, examining objects. You have to kind of know what you're doing to explore the objects with C++ because you have to dereference the pointer and then look through the tables. And potentially that could be simplified in the debugger. And the debugger refers to Haxe line numbers rather than CPP line numbers. But yeah, I mean the iOS debugger would be your first step, I would think. It's probably obviously more mature and yeah, probably useful. Same with Windows. Visual Studio is pretty good too. So
no, it's a great project. I was just asking for because there was anything that didn't that was blocked from using.
yeah, no. In fact, it should even work on a deployed device. Not connected to your dev computer, but you've got to compile with a debug flag on, so it includes all the instrumentation, which isn't going to be great for performance, amongst other things. So yeah, that's probably your reason why you wouldn't just sort of have it on all the time. It's just in a single file in the debug CPP file in the Haxe project, HXCPP project. So there's nothing real magical going on. It's just talking over a socket.
Hi. Does C++ 11 offer any solutions for performance improvement?
Yeah, I'm not sure about performance improvements. It has potential for making the code more readable with some of the Lambda stuff that it's got for closures. But as far as performance goes, I mean, I would still face the decisions about where to use dynamic and stuff, which is really the key to the performance. So I don't think it's going to help that much. It may tidy up some of the code, but performance I wouldn't expect to be significantly different. Unless, of course, they come out with, the new compiler versions come out with new optimizations as well, which are always a free bonus for us.
Right.